The final example I'd like to show before closing this screencast is that you can also do interpolation, 2D interpolation, with a function from the ndimage package in SciPy called map coordinates. Now, map coordinates is an interesting function that takes a little bit of thinking to understand how it does, in fact, do interpolation, or two-dimensional interpolation. This example will hopefully clarify some of that and allow you to explore your own interpolation strategies using map coordinates. The key thing to remember about map coordinates is that it only works on gridded data, equally spaced data. It can interpolate a low density grid to a high density set of points. Many times you want what RBF does and can do is just to take scattered data and create an interpolation function from those scattered data. Map coordinates can't do that. Map coordinates requires a gridded set of inputs, or an equally spaced set of inputs. So in this example, I'm taking an equally spaced set of data, 10 data points between -1 and 1 in each dimension. So the end result is going to be a 10 by 10 or 100 data points. Let me run this example so that the variables are available to me as we talk about them. Example 6.py, it will run and do its thing, and then I have x and I have y, and you can see what mgrid does, creates this gridded array of data between -1 and 1. And then the fvals is the function evaluated on that grid, and I'm going to show that underlying image in figure 1, and you can see that it's a low resolution image, but basically the same underlying structure as we had before, but it's on a sparsely populated grid. Now, to call map coordinates and use that to generate new data, and that's indeed what it does. Map coordinates, the other interpolation strategies, we created an object that could then be called with our underlying data. Map coordinates actually takes the original values and then the new set of coordinates at which to evaluate, and then generates a new two-dimensional grid. So it kind of does both all in one. So the interface is a little bit different with map coordinates, and that sometimes can be confusing when you're first encountering it. But it is pretty straightforward. So you can see map coordinates takes fvals, which are the original values at which I calculated the function. These are the sparsely samplated values. And then it takes coordinates. It actually takes an array of coordinates. So if I'm doing two-dimensional interpolation, this has to be two arrays. If I'm doing three-dimensional interpolation, this has to be 3 arrays of coordinates, and so forth. And these coordinates are index values. And this is the other confusing part of using map coordinates, is you have to somehow go from your new x and y values. Here I'm going to try to generate new samples on a grid from -1 to 1, densely sampled at 100 samples in each dimension. And I have to generate indices from those. And so I've constructed this little map to index function. And there's many approaches to this map to index function. But the key idea is to map my values from -1 to 1 to coordinate values in the original set of data, the original shape of the x and y data. Because the interpolation, the map coordinates, is going to assume that the original was exactly the same shape as fvals. Fvals, that the original coordinates is going to be anywhere from 0 to 10. Not inclusive. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth. Those are the original accepted coordinates. And now I'm going to interpolate to a denser set of coordinates. So if I look at I1 and I2, you can see that I1 and I2 go from 0 to 10. So it's actually doing a little bit of extrapolation. 0 to 10 on this new grid. And it's going to use, basically, it's going to interpolate to intermediate points in those coordinates. So when I do that, then fnew becomes this 100 by 100 grid with coordinates with values from the underlying fvals, but then interpolating those values. And the interpolation approach used is a spline filter, and it uses a fast spline approach, and that's why it requires equally spaced data, is so that it can do very rapid B-spline fitting and then construct the new coordinate values, the new function at the new coordinate values that are passed in. So as I look at and compare figure 1 to figure 2, figure 2 here will be, let's run this again and see if I can't get figure 2 to pop up. Show it. Let's see, where is figure 2? There it is. So figure 2 is the interpolated function, and you can see that it has been nicely smoothed out and interpolated, very similar to what the radial basis functions did, although this is taking an original gridded set of data to a more dense gridded set of data. So basically we've shown 3 different interpolation strategies for 2 dimensions using interp2D, the radial basis functions, and map coordinates. And which to use really depends on your situation, and the underlying algorithms are slightly different, and so if you have trouble with one of them, you might turn to the other. And my suggestion is to actually probably start with the radial basis functions, the RBF approach, and then if that doesn't do what you're looking for, or it's too slow, or there's other problems with it, then you can turn to some of these other interpolation strategies. And finally, we can see this Mojave plot that's also come up and show it. You can see there's a little bit of a hiccup in these data, basically on the boundary. It looks like between where the index 9 went to the index 10, sort of the extrapolation portion. But other than that, it's a nice looking plot, and it lets you see just a little bit of the power of the surf function in Enthought.mojave.mlab. If you have further questions or further information you want to learn about, go to the SciPy page, scipy.org, and there's a cookbook on interpolation that shows a little bit about some of the available interpolation strategies in scipy.signal, and also how to interpolate using fitpack routines to interpolate a curve. And here it's actually doing a little bit of curve fitting as well, instead of strict interpolation. And then documentation, you can also go to the SciPy reference guide, which has a nicely, it's coming along nicely, a chapter on interpolation that'll show 1D interpolation, spline interpolation, as well as showing how to use the radial basis functions. So I hope you've enjoyed the screencast, and I hope you continue to get a lot of use out of SciPy and the interpolation approaches inside of SciPy. Thank you.